right, so today we start chapter 13, which is the gas chapter. We're going to build up your picture of what a gas looks like, kind of. And ultimately, we're going to end by describing what's called the kinetic molecular theory of gases, which is basically the picture that we want you to hold in your mind when we're talking about a gas. And some aspects of this theory actually will carry over into solids and liquids, which we're going to do in chapter 15. But for now, the basic picture of a gas is going to be just that it's any gas, the air in this room, the helium in a balloon, any gas that you're talking about. The basic picture is that it's going to be individual particles, and for now it works to think of them as little spheres. And there's a lot of distance between those spheres compared to the size of these spheres. There's a lot of empty space on average between particles of the gas. There's nothing in there between them. And these particles are moving around all the time. They're zooming around. So, maybe imagine a balloon, right, with helium in it. That's a pretty simple picture if you forget about elasticity. So there's a bunch of little helium atoms zooming around the side there. They go pretty much in a straight line until they hit something. The only thing that they could possibly hit in there is either another gas particle or the inside of the wall. And they go in a straight line until they hit something, bounce off. Okay? And they don't lose any energy when they hit stuff. Okay? That's the picture that we're going to have for now. It's not quite true. There can be a transfer of energy, particularly when it hits the inside of the wall. You can transfer some energy out. But we're going to ignore any of that energy loss. So for now, we're going to keep the total energy the same. Okay? So you guys, that's basically the picture. Little tiny particles moving around in straight lines, a lot of space between them on average. They hit something, they bounce off, but there's no total loss of energy. Kind of like pool balls. You can hit the cue ball into another ball, and some of that energy, that cue ball, is transferred into the energy of the ball that it hits. But if you add up the energies of both of those, then in our picture, it would be the same before and after. Okay? Now in real life, like with those pool balls, that's not the real picture because some of that energy is lost, right? There's some friction with the table, resistance with the air, sound, right? Some of that energy goes other places. We're not going to think about any of that. We're going to keep the total energy the same. And it ends up that in order to describe a gas, okay, we need to know several things about it. Things that we kind of already know about. The volume of it, we need to know the temperature of it. I'm going to talk about temperature a little bit more carefully later on. We need to know how much gas there is. Usually we're talking about moles there. You guys know about moles. We need to know about the pressure of the gas. Now I haven't talked about pressure much so far, so I'm going to take a little bit of time to make sure that you know what I mean when I say pressure and what it means. First of all, the definition of pressure. Force over an area. Force is generally mass times an acceleration. Because we don't do calculus in here, we're going to describe acceleration. acceleration this way as change in velocity over change in time. The delta means the change to the difference, right? The velocity after minus the velocity before, right? The same delta we've been using. And over however long it takes for that velocity to change. You guys okay with these definitions? Have you seen them before?
Yeah.
Okay. Good. And then velocity, we're just going to do one dimension. But the same result translates directly over into 3 dimensions. It's change in position with respect to time. So, what that means is, and you guys know what area is, right? It's the surface area. For something to apply a pressure, it has to apply a force over some area. To apply a force, it has to have mass and it has to undergo some acceleration. When we say acceleration, we include deceleration too, right? In other words, its velocity has to change. It can increase or it can decrease. And that means that its position has to change with respect to time. So in our picture that we have of the gas, all these particles moving around straight lines until they hit something, if you imagine them hitting the inside of that balloon. That particle of gas zooming along, hits the inside of the balloon, and then changes position, which means that it's going to accelerate. The velocity is going to change, right? If it's moving along at some velocity, whatever it is, it hits the inside of the balloon, it's going to stop for just a second, and then it's going to bounce off, okay, with the new velocity. Maybe the velocity it had before, but it's going to change. It's going to go this way, and might be negative, right? Make sense? You guys buy that? Watch. I like this one. So imagine see this piece of chalk right here? This is one of those helium atoms inside of that balloon. Watch out, Julie. And this is the inside of the balloon. We're inside the balloon, right? And there's the inside. Leave the mark. Can you see that mark?
Yeah. It's special.
Yeah, that's it right there. Right?
There's like 2 dents up there.
Yeah. I've used that before, I think. You find us in? So, okay, this helium atom, when it hit the inside of this balloon, right there, that dent, let's call it this one right here. You guys see that? Okay. That's the area that it hit. It had some velocity before it hit, and then it bounced off, right? So its velocity changed right at that instant. It was moving, so it underwent some acceleration, which means, and it has mass, so it applied a force over that area, that dent in the paper, right? Which means that it applied a pressure on the inside of this balloon. You guys kind of get that picture? And so in that balloon filled with helium atoms, there's 10 to the 23rd of them or so, right? And so at any given instant, some fraction of that number of helium atoms is going to be doing just that. It's going to be hitting the inside of the balloon because each atom has mass and it's changing its velocity. It's undergoing acceleration when it hits the inside of the balloon, which means it's applying a force over that area, which means it's exerting a pressure. So an atom of helium doesn't weigh much. Its mass is really small, which means that individual pressures are really small. But at any given instant, a lot of those atoms, helium atoms, are going to be hitting the inside of the balloon. And we add them all up, that's the total pressure inside of the balloon. Kind of makes sense? We can, okay. The atmosphere, it's basically a bunch of gas, right? It means that same picture that I'm trying to develop for you, these particles moving around all the time, it applies to the atmosphere. Thing is, there's, you know, a lot of gas up there if you extend all the way to the end of the atmosphere, how far that is. And it's being held, it doesn't fly off in outer space because of gravity, right? Gravity attracts the gaseous atoms in the atmosphere, pulls them down. It not only does it keep them from flying off into outer space, but it also means that they're being accelerated. Right? Gravity is a force, but there's an acceleration due to gravity, g, right? You guys know about g? 9.81 or so meters per second squared. That means that these gas particles basically are being accelerated down. They have mass, so they're applying force, right? Which means that each one of those, okay, imagine like a swimming pool or something, right? On top of that swimming pool there's some surface area, right? And on top of that surface area, each one of those particles, gases is applying a force, right? So there's going to be a pressure. That makes sense? So the atmosphere is exerting a pressure on top of that pool. Also on you, right? The atmosphere is exerting this pressure on you. How come you don't feel it? Because you're used to it, because you're strong. No, so I heard somebody say something about the body.
It's because your body's putting pressure outward.
Exactly. There's also pressure inside of your body that's the same as the pressure outside of your body, right? So that pressure that the atmosphere is exerting out here is exactly balanced by the pressure inside of your body pushing out. So it doesn't feel like anything because it's at equilibrium, right? If that makes sense? If you go up to Yosemite or to Tahoe, your ears pop, right? That's because the further up you go, the less atmosphere there is above you. The less atmosphere there is above you, the less pressure there is exerted on the outside of your body. It takes your body a while to adjust, right? So at first, down here in Modesto, we're like, 100 feet above sea level or something like that, right? Pretty close to there. As we go up, less pressure out here, there's still more pressure pushing out. So your eardrums get popped, right? Not popped, but pushed out. And then coming back down, right? But after a while, it goes away, right? So that means the pressure inside of your body has equilibrated. Now it's the same as the pressure outside up there at Yosemite. When you come back down, then as you're coming back down, now there's more and more pressure outside of you, and your body hasn't equilibrated yet, so there's less pressure in here, and so it goes the other way. It still feels like your ears are stuffed up. That's because the pressure is pushing them in now until it equilibrates and everything's good again. We can measure the pressure exerted by the atmosphere if we use, if we use a barometer. And we have one of these in the lab. These are really old. There's a lot of different, better ways actually to do it now. This one involves a big pool of mercury, which is not really a good thing. But it works like this. There's this pool of mercury, and if you look in our lab and go in there, it's on those shelves right by the door where we come in. If you look at it, there's a cup about that big, and it's full of mercury. And there's this glass tube, and that glass tube is open at the end, and that's submerged within the mercury, closed at the top. And before they put that glass tube in there, they evacuated it. That means they pulled a vacuum on it. They pulled all of the gas, all the air, everything out of that. So there was no gas in there at all. Just pretty much a vacuum. So what happens is the atmosphere, like as I described, is exerting this pressure on the surface of this pool of mercury. Pretty much the same all the way around. There's no, and if this tube weren't in there, then it would just, be a pool of mercury, a pool of water. But because that glass tube is in there, right here, there's no pressure being exerted down. Now it's in, the forces, the pressures aren't balanced. Right? You guys follow? So that means that the liquid in here is going to go where there's, least resistance. It's going to be right here. So the atmosphere pushes down here, all over, and the mercury rises up in this column. It goes up and up and up and up. But as that column of mercury gets higher and higher and higher, it has some mass also, right? This column has some mass. And gravity's accelerating it down. So right at the base here, there's a force being exerted in the opposite direction that the atmosphere is pushing, and it's going to be down this way. Does that make sense? And that means there's a pressure being exerted opposite the pressure due to the atmosphere. At first, when you first set this up, atmospheric pressure is going to be greater than the pressure exerted by the column. It's going to keep on rising. The higher it gets, the more mass there is in there because there's more mercury in there, right? It goes higher and higher and higher. The pressure increases until the pressure at the base here, exerted by the column of mercury, balances the pressure exerted by the atmosphere. That makes sense? If we change the atmospheric pressure changes because a high pressure system or a low pressure system is moving in, or for whatever reason. When this changes, then the height of the column of mercury will adjust to balance that outside pressure. And so the height of this column of mercury is one measure of atmospheric pressure. And it's not only that, it's not only a measure, it's also one of the units of pressure. And it ends up that, the pressure changes. All these storms coming in, the pressure changes in advance of those. But on average, it's about 760 millimeters, right? Less than a meter, right? About 3/4 of a meter. What we're going to do now, what I'm going to do for you is I'm going to develop the equation that describes the pressure exerted by a liquid in a column, which describes this, the column being a cylinder. That is pressure right here, exerted down. To do that, the volume of the cylinder is just the height times the area. No big deal. Mass is it obvious what these symbols mean, or should I H is height, A is area, B is volume. The mass is the density times the volume, right? Density is mass over volume times volume is mass, right? The force applied by that liquid at the base of the cylinder is mass times acceleration. And here, because the acceleration is not due to gravity, it's mg, right? Mass times acceleration due to gravity. Pressure at the base is the force times the area. What I'm going to do now is I'm going to substitute in these expressions. Here for the volume, I'm going to put height times area. Here for the mass, I'm going to put density times height times area. The x's are just times. Do you like that, or do you like this parentheses better? No? Never started using this. I know, I'll use dots. You guys following what I'm showing you? Mass is density times height times area. That means the force, plugging this in for the mass, is density times height times area times g, which means the pressure is this, but the areas cancel, right? Doesn't matter which order you write them. So this expression here describes the pressure exerted by a liquid at the base, inside a cylinder at the base of that cylinder, like the barometer. And notice, okay, that it's equal to gravity, the constant, times the density of the liquid in there, times the height. What this says is that the pressure exerted at the base, one thing that it says is that if we had a silo full of mercury, right? Something where the diameter is about the length of this room, right? The pressure exerted at the base of that silo by the mercury is the same as the pressure exerted by the mercury at the bottom of the barometer in the classroom, or if the cylinder is just this big. It doesn't matter how big the cylinder is, just how high the mercury is in it. That makes sense? The pressure exerted at the base of this much mercury, right, is the same as the pressure exerted by the base of this much mercury, as long as the height's the same. That's okay? Okay, it's true. So that's one. You're going to want to know this equation. One of the things that we can do is we can calculate the pressure, but more useful to us is we can figure out how high a column, if we know how high the column of one liquid, like mercury is, at a certain pressure, we can figure out how high the column of a different liquid is under the same external pressure, as long as we know the densities. I'll show you how.
Yeah, the gravity and everything else is also. If you look at the equation, the higher the height, the more pressure. Notice if the gravity is different. But if it's higher, then it's gravity density is relative. We'll kind of get it's over here. There, let's say this is going to be the causing the gas. Creating pressure. That's the pressure. Pressure goes up, but its height goes up. I've heard about this explained.
Does gravity ever change?
Does what?
Gravity ever change?
We're gonna assume it's constant. Is that a trick question? Yeah, it does, depending on how far you are, where you are in there, but not enough for us to care. But we're gonna keep this constant. And, you know, we'll always be on Earth. So. So you guys got it? What do you think? How do you wanna do this?
Can you write the gravity constant up there?
Can you do it? We don't need it.
Oh, because it's the same on both sides.
It's like,
Are we ever going to need
I don't
it?
believe you, Steve. You don't believe me. All right, let me show you. Okay. Here's what we're going to do. The pressure column of mercury is just equal to G times the density of mercury times the height of mercury. That's just the equation I developed a minute ago. The pressure of the water barometer is equal to G times the density of water times the height of the water barometer. Thing is that, you know, that atmospheric pressure is the same, so we can set these equal to each other. You guys see that? Make sense? So that means we can say you guys see what I did there? I just wrote out our expression for the pressures, right? One thing that we see is that G cancels. We are assuming that it's going to be constant all the time for us. So that cancels. And what we want is the height of the column of water. So rearranging this. we know everything in here, right? I gave you the densities of both of the liquids. What's the height of the mercury column? 773 millimeters, right? Because the pressure is 773 millimeters of mercury, that means the height of that column of mercury is 773 millimeters. Right? Yes, good. Travis, you don't like that, so.
Well, millimeters is the measure of all.
Yeah, no, that's a good thing to think about, right? So millimeters is a unit of distance, right? But what I was trying to show earlier is that because that column of mercury, that barometer that I was describing, changes with the external pressure to balance it, that we use the height of that column as a measure of external pressure. So that's the first unit of pressure that I've given you guys, and that is the millimeter of mercury. Is that okay? So that's, so density, mercury. Notice that in this type of problem, because we're taking one density over the other, it doesn't really matter what units they are as long as they're the same units. They definitely have to be the same units. So we get like 10,500 millimeters. Let's just give you a picture. So that's the answer, at least in those units of millimeters. But how is that? Well, let's see. .5 meters, right? You know how high a meter is? Like about a yard, right? It's about 3 feet. It's like more than 30 feet, right? So the barometer, the mercury barometer, it's, you know, about three quarters of a meter, right? Maybe this tall, right? Whereas the water, it's way up there. It's 30 feet or more than 30 feet, right? So that's why, at least in these old barometers, we use mercury, because it's the densest liquid that we can use, right? There's other ways to measure pressure now, but I believe there's a homework problem or two that asks you to do this sort of thing, so there you go. Okay, well, so I guess we could use millimeters of water as a pressure unit, but we don't. There are other units. The SI unit of pressure is called the Pascal. Pascal is a joule per cubic meter. which is a kilogram per meter second squared. Is that? Torr. Same as a millimeter of mercury. Atmosphere. There's a list, there's a table. So instead of writing them all down, there's a table on page 425, table 13.1, and you should know it. It's definitely useful to be able to convert between units of pressure. So that's pressure. That's the picture that I'm hoping you guys can keep in your minds as we go through this. What your book does next is it goes through a few of the steps in the historical development of the ideal gas law. I'm assuming everybody here, because you've all had chemistry before, have seen the ideal gas law. Is that a good assumption? Or is it a bad assumption? Bad? You've never seen the ideal gas law? Don't remember?
I can't recall it.
So I'll just pretend that you've never seen it before. So this guy named Boyle, did some experiments, really clever experiments, and he figured out that for a gas, as long as we kept the amount of gas constant and the temperature of the gas constant, there's this simple relationship. That is that the volume and the pressure are inversely proportional. In other words, that when the pressure increases, the volume decreases. When the pressure decreases, the volume increases, and vice versa. When the volume increases, that means the pressure is decreasing. When the volume decreases, the pressure is increasing. Inverse relationship. Then this guy named Charles. That's his last name. Rich Irish guy, I guess. Figured out the relationship between volume and temperature.
Yeah, they're inversely, yeah.
And you guys know that sign, right? It means proportional to. No? If you don't, think of it as being, saying that in this case, in Boyle's law, we can say that the volume is equal to some constant times 1 over the pressure. That's all that means. And the same thing for Charles' law. Volume is directly proportional to temperature means that we can think of the volume as being equal to some constant. These aren't different, these are different constants. I guess I'll label this with sub B for Boyle, sub C for Charles. Times the temperature. There's an interesting result of this relationship here. This way. Everybody's seen this, the equation for a straight line, y equals mx plus b, where y versus x, m is the slope of the line, b is the y-intercept. Well, that's what this looks like. If y is the volume, if x is the temperature, that means with a slope, with a y-intercept of 0, the slope is going to be whatever the constant is. And remember, this, okay, for here, I didn't mention it actually. The amount and pressure have to be held constant. They show some graphs in your textbook on page 428. I think they showed 3 lines. It's the same gas, it's I think air, right? And I actually think they keep the amount the same, but they're just at different pressures, I think. Oops. But when the pressure and or the amount changes, the slope's going to change, right? Still at the same y-intercept of 0. One of the things that came out of Charles' law is that because at that time they were using the Celsius or the centigrade scale, they can only get down so cold. They didn't have real good cryogenic equipment back then. But see, this is degrees Celsius. And this is 0 right here. Then you get down to maybe somewhere maybe down there somewhere. They had a bunch of points up here. So they did what you guys do in lab when you have a straight line. They drew the best fit straight line. Then they extrapolated those straight lines. They saw that they all crossed the axis at the same spot. And that ended up being minus 273.15. And that's where the volume is 0. Okay? And so what that said is that gave them absolute 0, right? That's what we call absolute 0 now. It gave us the Kelvin scale. That's what 0 is. So that gave us the Kelvin scale. If we take 273.15, this is negative 273.15, and we add it to the Celsius scale, we get the Kelvin scale. So it's 0 here, and everything else is higher than 0. We'll talk about what it means for it to have a volume of 0. It couldn't really, but we'll talk about that later. it gave us the concept of absolute zero, and it gave us the Kelvin scale. It also gave us the ability, which was more important back then than now, but still interesting, to make what's called a gas thermometer, a way of measuring temperature based on the volume of the gas. Let me show you how that works.
This turns out to be constant, doesn't it? I always using this one.
Yeah, that does turn out to be a constant. That's absolute zero.
He said.
This is the equation of one of these lines over here, as long as we're using the Kelvin scale. The Kelvin scale is what gives us the zero y-intercept. Right? If we have a gas, two different temperatures, we're going to keep the amount and pressure constant. The way you do that is pretty simple. You take a tube, open at one end, closed at the other, and you drop a plug of something like mercury into it. That mercury slide down in that tube until the air that's in there, okay, is compressed enough to where it can't go down any further. Do you guys get that picture? It's not going to go all the way down. See, it's sealed all the way. There's air in here, right? So you just have a tube, glass tube. It's closed at one end, open at the other. Take some mercury, drop it in the top. Okay, the mercury, because it's liquid, it's going to press out against the sides of the inside of that tube, that column. So there's no way that the gas that's already in there can escape past it. So it's going to push down that gas until, it's going to compress it, right? Until that gas is pushing back to where that mercury's not going to fall any further. You guys get that picture? That's going to be, before we do that, when we take this tube and put it somewhere where we know what the temperature is going to be, one of the things that we know is what's called the ice point, the temperature that ice melts and that water freezes. Right? So let's put it in a bucket of ice water. Okay. We know the temperature there. In kelvins, that'll be, it's 0 Celsius, right? Which is 273.15 Kelvin. The whole way this gas thermometer works is you have to know one temperature initially. And, as long as you know, like what temperature ice melts at or something like that, which we know, then we're good. So we put that gas thermometer where the temperature is what we know, and we have marks on the side of it. Right? It's like kind of like a burette. It has marks so we can measure the volume. So we look at that and we see what the volume of that gas inside here is. Well, that's our V1. because it's open to the atmosphere out here, right? The pressure on it, it's always the same. Pressure's constant. That's one of the requirements. And because none of the gas can escape past that plug of mercury, the amount of gas in there is constant. That's another requirement. So that means that if we rearrange this a little bit, we get V1 over T1 equals C. So the volume in here times its temperature is equal to some constant. And then what we're going to do is we're going to take that out and put it somewhere else that's at a different temperature. So that means the volume of the gas is going to change. That's what Charles law tells us, right? And it will. It's going to have a new volume. We can measure that. We can look at it. But it's going to, V2 over T2 is going to be equal to the same constant. The C is the same because it's the same pressure and the same amount of gas. Are you guys still with me? Two expressions equal to the same constant, they're equal to each other. Right? So we don't care what that constant is because it's gone away now. What we can do is now we can rearrange this, solve for T2. You guys see what I did there? So now let's go back to the experiment. Same gas thermometer. I don't know, let's put it in something else that's warmer, I don't care. Warm water. Could be colder too, it doesn't matter. Because it's warmer, this is the volume now. It went from this volume here to this volume here. We can just read the volume by reading the marks on this gas thermometer. Now we know V2. We had already read V1. We know what T1 is because we set it up that way. This is the ice point. Plug everything in, that tells us what the new temperature is. For example, let's say that initial volume was 22.34 milliliters. V2 was 59.6. Plugging in there. You get it. Let's not make it that soon. Let's make it 29. at 364.7 Kelvin, or in Celsius. .6 Celsius. So that's how you make a gas turbine. That's how you do the calculations. And I believe you'll see a homework problem like that too. All right, so coming back to the sort of historical development. We know that volume is inversely proportional to pressure. Volume is directly proportional to temperature. And then along came Gay-Lussac's law, Avogadro's law, and we found that volume is directly proportional to the amount of gas in there. The symbol we use for the amount of gas is N because usually we're talking about moles. So as long as the pressure and temperature held constant, Gay-Lussac found that there's a direct proportionality between volume and amount. Or, volume is equal to some constant times the number of moles. If we put all these three together, does this make sense? If it's proportional to N when P and T are constant, when it's proportional to 1 over P when N and T are constant, and when it's proportional to T when N and P are constant, then altogether, volume must be proportional to N times T over P. And now we're going to write this a little differently. We're going to use the constant of proportionality, call it R, because that's what they did. R times NT over P, or rearranging this. PV equals nRT. This is called the ideal gas law. Called the ideal gas law, not because it's ideal, but because it talks about, it describes what is called an ideal gas. And I'll explain the difference between an ideal gas and a non-ideal gas in more detail towards the end of the chapter. But basically, an ideal gas is one where the gas particles themselves don't take up any volume. There's no, like as I described earlier, there's no loss of energy between the particles. When they interact, they don't lose any energy. which means that, I'll explain what that means in a little bit. But basically, there's no such thing as an ideal gas. If you think about it, one of those things is that, I said the gas particles themselves don't take up any volume. And that can't be. They have mass, right? They occupy space, right? They're matter, right? Every atom of the gas takes up some space. Might be a little bit. Most of that picture that I built, that I described at the beginning today, most of that gas in that balloon is empty space because these particles are really far apart from each other relative to how big they are. But there's still some of that volume inside that balloon taken up by those helium atoms. What we're doing here with the ideal gas law is assuming we're neglecting that volume taken up by the gas particles. We're also neglecting any loss of energy due to any interactions. Because see what happens is, remember that helium atom that hit the inside of the balloon here? Okay, if before that helium atom got to the inside of the balloon, it had lost some energy to another atom, it would have been moving slower when it hit the wall, which means that its acceleration would have been less. Its force would have been less. The pressure that it exerted would be less. So in a real gas, we'll get to this later, there is actually some interaction between the particles. They lose some energy, and they don't quite exert quite as much pressure as a gas would if it didn't have any interactions. So, and we'll refine that a little bit later on. But this is what we're going to use for all gas law problems, unless I specifically say that it's not an ideal gas, and I'll show you how to deal with that towards the end of the chapter. It ends up this constant, R, the gas law constant. It's going to be one that you're going to want to know if you don't know it already. It's in 4 different units. In table 13.2 on page 434, you should know them all. If you have that, the units of the gas constant are depend upon what units of pressure you're using. If it's pascals, then it's going to be the 8.314 or so, and the units are joules per Kelvin mole. All this stuff's in that table. If the pressure is in bars, that's another unit of pressure, in table 13.1, and it's 0.08314,472 liters bars per Kelvin mole. If it's in atmospheres, then it's 0.0820575 liters atmospheres per Kelvin mole. If it's in torr, then it's 62.3637 liters torr per Kelvin mole. There they are. So, for instance, we can use the ideal gas law to solve this problem. Write it down and then look at it and think about it. So, it's a gas. I'm asking for a pressure. So even if you weren't in this section, you didn't know where we were, just on a track somewhere. Hopefully you'd start thinking ideal gas law. And we're asked to calculate the pressure. So rearranging the ideal gas law, which means that we need to know, okay, R, just look it up in the table, memorize it. We need to know the temperature. I gave you the temperature. We need to know the volume. Well, I told you it's a sphere, and I gave you the diameter, so we can calculate the volume, right? Volume of a sphere is 4/3 pi r cubed. And the number of moles, the amount. I told you what gas it is and how many grams. We can use the molar mass to find out the moles, right? So if you look, when you look at those units of the gas law constant, you'll notice that they all have Kelvin in them. The temperature in an ideal gas law problem always has to be in Kelvin. Typically, you're given it in Celsius because, as you notice, the thermometers in your lockers in the lab, they're Celsius, right? So most of the time you see Celsius thermometers. The volume, it's always liters, right? This is moles. The value of R you use affects what they're given to pressure, right? If you're already given the pressure, then usually you use the R that's going to match that pressure. Let's do atmospheres. The 273.15. In your textbook, they round it to 273. I'm asking you to use 273.15. Treat this as an exact number when you're doing that too. guys check that in your calculators, please?
That's correct.
Let's see, units. We have N in moles, T in Kelvin. What units did I say we need volume in? Liters. Go from meters cubed to liters. That's the conversion. There's 0.001 cubic meters in a liter. What I'm going to do now is I'm going to take this for N, this for T, this for B. For R, I said atmospheres, so let's see, the units work out this way. Kelvin, and Kelvin cancels. Moles, moles cancel. Liters and liters cancel in atmospheres. So this would be collapsed if it were an atmospheric pressure. Zero pressure. Pick up there on Wednesday.